It was these drawbacks of having an identifiable, centralized, ledger-based system of value exchange and the introduction of the internet that made some start looking at the promise of digital money. The promise of a totally decentralized currency is that it takes away the need for a bank or financial institution to stand in the middle. By doing so, we might be able to access the estimated 1.7 billion people on the planet who are underbanked. It should, in theory, also allow faster and easier cross-border transactions, reducing inefficiencies by speeding up transactions and reducing costs. However, there are problems with decentralized digital money. The first and most important one is the double spend problem. In its simplest explanation, I would like you to think of an example where your friend owes you $10. She offers to take a picture of a $10 bill and send it over to you from her smartphone. Now, even if you were willing to accept that photo as repayment of her debt, the double spend problem exists because there's nothing preventing your friend from also sending that same picture to someone else to repay them without telling you. This problem doesn't exist with paper money because if the transaction is in cash, there's finality, as once you have that $10 bill in your possession, your friend no longer has it, so she cannot double spend with it. Similarly, with a bank transfer, for example, once the money has been moved into your account from your friends, they cannot take the money back without your authorization. Bank transfers also require a centralized party to debit your friend's account and credit yours. Now, this leads us to another problem inherent with decentralized digital money: security issues. Digital networks are hackable, as recent cyber attacks in the US and countless billions lost in cryptocurrency fraud to date have amply demonstrated. If we were to extend the example of your friend sending you a picture of that $10 bill, it's possible that someone may electronically intercept that transmission. That same problem would not exist if your friend were to hand you a $10 bill, or they were to instruct their bank to transfer the money to you. Both shortcomings of decentralized digital money can be addressed by some centralized, trusted party. However, that defeats the purpose of decentralizing the movement of money digitally. Also, having a centralized, ledger-based party introduces risks, such as a single point of failure, potential censorship of users, and whether the party itself is corruptible. And that's why Halloween in 2008 was so meaningful for the world of cryptocurrency, as it was the birthday of Bitcoin and all the modern cryptocurrencies that have come after it. A person or organization going by the alias of Satoshi Nakamoto managed to address the key problem of double spending using a consensus-driven, decentralized ledger for peer-to-peer value transfer over the internet. According to his white paper, this electronic coin is a purely peer-to-peer version of electronic cash that would allow online payments to be sent directly from one party to another without going through a financial institution. It also solved the double spend problem by using a decentralized ledger that anyone was able to access in order to verify that the Bitcoin received had not already been spent by the holder. It did also make it very difficult, although not theoretically impossible, to alter the decentralized ledger, as any modifications needed to be cryptographically proven, hence the term cryptocurrencies. The simplified version of the Bitcoin premise is based on the following process. Number 1. Once a transaction between two Bitcoin users have been agreed, an owner of a Bitcoin digitally signs the Bitcoin over to the next owner using their digital keys. Step 2. A block that includes the transaction is created, and in order to prevent an owner from double spending the coin, the receiver would need to confirm that the previous owner did not already sign over that same Bitcoin to someone else earlier. Number 3. The block including the transaction is sent to all participating computers running Bitcoin software in the network, and these computers are called nodes. Next, each node races to search for a correct answer to a complicated computation to validate or authenticate the block. This process is called proof of work. In step 5, the first node to solve the computation and validate the block is rewarded with new bitcoins. And this is where the term Bitcoin mining comes from. The difficulty of solving these computations increases over time. Once enough validations have been received about that particular block, the block and the transactions contained within are added to the blockchain. This process of getting validations from all the nodes is called consensus. Next, the block is added to the decentralized ledger, appending it to the chain, and that's where the term blockchain comes from. The longest blockchain is the one that everyone takes to be the correct one, as it's had the most proof of work done on it. Any false transactions that don't get enough confirmations are just discarded. And lastly, previously confirmed blocks are very unlikely to be undone, as that would require an attacker to create a brand new chain and redo all the proof of work quickly enough to overtake the longest chain. Now don't worry if you don't get this right away, as we'll dive much deeper into how nodes, blocks, miners, and proof of work actually works. Nonetheless, if you're interested in reading Satoshi Nakamoto's white paper, you can find it at bitcoin.org.